With me is Jasmine Mancuso, and we'll be your hosts for the webinar. If you're tuning in, you likely are aware that New Zealand mud snails have relatively recently been found in inland rivers and streams of the Great Lakes, raising concerns about their further spread and the potential impacts on local aquatic systems. This webinar series, brought to you by the Great Lakes New Zealand Mud Snail Collaborative, aims to improve our knowledge on ecosystem impacts of mud snails, develop strategies to minimize their spread, inform management initiatives, and raise public awareness. To know more about the collaborative, you can visit the website at www.nzmscollaborative.org. And to become more involved, you can email info@nzmscollaborative.org. Just a couple housekeeping items before we get started. Please keep your microphones muted so we don't interrupt the presentation. We'll leave time for questions following the presentation. If you have a question, feel free to type it in the chat box. Jasmine will be compiling them and we'll read them aloud once the presentation has ended. In the event we can't address all the questions within our time slot, we'll follow up with individuals post the webinar via email. And lastly, the webinar will be recorded and available to view and or listen through the website. You can also find access to the webinar by emailing info@nzmscollaborative.org. All of our past webinars are available for viewing on the website as well. With that, I'd like to thank Dr. David Hammond and introduce our speaker today. David Hammond is Vice President of Applications Development for Earth Science Laboratories, Inc. Dr. Hammond has 4 patents, a half-dozen peer-reviewed publication, and is an environmental chemist who has consulted to private industry on topics including pest management, taste and odor problems, biological wastewater treatment, sustainability, and biomimicry. He holds a master's degree from the Energy and Resources Group and a PhD in environmental chemistry, both from the University of California. Dr. David Hammond's talk today is called Eradication of New Zealand Mud Snails from a State Trout Hatchery. And I will hand it over to you, David.
All right, thanks, Jeremy. There we go. Sorry, just getting set up here. I'm assuming everyone can hear me and
I can hear you loud and clear.
Trying to take myself off the screen so you get the full, are you guys seeing me in the corner?
Yeah, we can see you right now. I think if you just click on that start video.
Oh, here we go.
Get you off there. Perfect.
All right. Thank you. All right. Well, thanks everyone for the opportunity to share with you some experiences we've had from the field dealing with this important invasive species. I'll be sharing with you a couple projects, but the main one is about a fish hatchery in Arizona, near Sedona, Arizona. It's called Page Spring. And at the risk of ruining some of the suspense, I'll just share with you at the beginning here some of the project highlights. Our approach has been to use a low dose of a compound called EarthTec QZ that's formulated in the ionic form of copper, cupric ion, the Cu++ form of copper. And our approach has been to use a low dose for a long exposure period. We found that that helps avoid impacts on non-target organisms like fish. The dose rate that we ultimately ended up using for this project was 30 parts per billion as copper. That's a half a part per million as the product. The treatment period lasted 50 days. The overall chemical cost was $5,500. And we believe that the eradication was successful. It's hard to prove that something's not there, but it certainly seems to have been successful. So with that, I'll delve into some of the details. I assume most of the people attending this seminar or webinar have probably more knowledge about New Zealand mud snails maybe than I do, but so I won't belabor the background on this, but in case some of you don't, just cover a few basics. New Zealand mud snail is native to New Zealand, of course, and surrounding islands. But it's one of the reasons why it's so aggressive as an invasive species is that it's parthenogenic, meaning that it reproduces asexually. It's the females are born already carrying developing embryos. They can have 4 life cycles per year, and that makes them very prolific. They're also tough as an invasive species because they possess an operculum, which means that they can close up and resist their environment. So even if they get swallowed by a fish, they can actually pass through the gut of the fish and come out the other end unharmed. These are some features for identifying them and distinguishing them from other species. I'm not going to spend time on that. Just it's worth noticing that they are very small, and they can have very high densities, up to 500,000 individuals per square meter. They also, due to their aggressiveness and the high densities, they tend to overtake and outcompete native mollusks. So in the case of the Snake River, where they were first found, there are now 5 native mollusks that are listed as endangered as a result of just being outcompeted by these aggressive mollusks. And there's also beginning to be measures of impacts on some of the other species, such as mayflies, stoneflies, caddisflies, and chironomids. So again, they're originally from New Zealand. They were first found in the US in the Snake River in 1987. They since expanded their range to some of the surrounding states and the Colorado River by 1995, and have since spread through some of the northern states. And as you know, they're beginning to appear around the Great Lakes region. They were first detected in Arizona in the Colorado River, but this incidence of detection in October of 2019 was the first known discovery of New Zealand mud snails in Arizona outside the Colorado River. The Page Springs Fish Hatchery is just outside Sedona. It's about 82 acres. And the configuration is that the water comes from a spring up here at the northern end. The spring's hidden in the trees here. The water flows south through the raceways, and then circles back north to a little show pond before it discharges to a creek adjacent to the hatchery called Oak Creek. This is Arizona's largest hatchery. It produces 57% of the total fish in Arizona hatcheries. That's approximately 218,000 pounds a year. It's mostly rainbow trout, about 95% rainbow trout, and a small amount of brown trout. And the total value of the hatchery production per year is in the range of $185 million. It's unknown how they were introduced into this hatchery. There's speculation that they could have spread from the adjacent creek, where there have been some eDNA tests showing positive, and there are fly fishermen that do fish in Oak Creek. And possibly, if they are in Oak Creek, then they could have been spread by an animal into the hatchery. But I think more likely it was humans. There were people working for Arizona Game and Fish who were sampling in the Colorado River, and then came up to the fish hatchery to practice some tagging techniques, tagging the fish. and it seems most likely that that was the vector, but it's uncertain. In any case, once they were detected in the hatchery, they were faced with a pretty tough decision: either eradicate the entire fish stock and drain and sanitize the entire hatchery, or look at some method to eradicate them without shutting down the hatchery, and just hoping to spare as many of the trout as possible. And that latter alternative is the one that they selected, and selected as well to use EarthTec QZ. EarthTec QZ has been around for about 7 years, since 2013. It started out as an algicide and a bactericide, and then people noticed that it was working also against quagga and zebra mussels. And since then, we have had experiences in quite a variety of different environments, doing rapid responses, which is going into a lake where invasive species are discovered, trying to go in quickly and treat the small area where they were discovered and knock them out before they can spread to the rest of the lake. We've also done a handful of full lake eradications, the largest so far being 29 acres and over 100 feet deep. And then we've had numerous experiences working directly in fish hatcheries. And that was the experience we drew on most for this project. And I'll share with you one of those. This is a fish hatchery in Oklahoma, outside Oklahoma City. And they pull water from Lake Hefner, which is infested with zebra mussels. And so their supply to their fish ponds is constantly bringing in, at least at the risk of bringing in, veligers and contaminating their fish ponds. They discharge then to a creek at the upper left-hand corner there, and that creek was not known to have any mussels, and so they were eager to prevent the spread of mussels to that creek. So they came to us with the treatment goal of eradicating the mussels present in the fish ponds prior to discharge. And we developed a protocol using about 5 parts per million of EarthTec QZ as product, which is equivalent to, that's a typo there, it should be 0.3 milligrams per liter as copper, or 300 parts per billion as copper. So that's the dose that we used in these ponds with the fish present to decontaminate the water prior to draining the water for harvest of the fish. And what they found was that the fish tolerated that dose of ionic copper quite well. In fact, the managers even commented that the fish were healthier than before, presumably because it was controlling bacterial diseases on their gills and fin rot and gill rot. But also they noted that often when they harvest the fish in a situation like this with that much algae present, those floating mats of algae will trap the little fish at the time of harvest, and they'll lose some of their yield. So by treating for 5 days before harvest of the fish, this is a photo taken not 5 days later, this is a different time of year, but it just shows you the difference. When there is no algae present, it's much easier to drain the ponds. They get a better yield of fish. They don't lose any fish to getting trapped under the algae. And as far as we know, it's been successful at eliminating live mussels from the water that they're then discharging to the creek. So that was some of the knowledge that we based this treatment on, coupled together with some data I had from a lab. The fish in the Page Springs hatchery, being trout, are more sensitive than the fish at the Oklahoma City hatchery. Rainbow trout, as salmonids, are among the most sensitive fish to copper. And I had previously contracted with a third-party ecotoxicology lab out of California called Aquatic Bioassay and Consulting to test EarthTec QZ against rainbow trout and find out the LD50, LD95. And what they found was interestingly, the 4-day toxicity was virtually identical to the chronic 21-day toxicity. And the NOEC, which stands for no observed effect concentration, was 4 parts per million as EarthTec, equivalent to 240 parts per billion as copper. So in this measure, the effect measured was mortality. So the highest dose at which no mortality was measured was 4 parts per million as product and 240 parts per billion as copper. So that was the information we had coming into the project at Page Springs, and we determined that we'd start with 90 parts per billion as copper as a safe rate to treat for New Zealand mud snails, and just maintain that rate for as long as necessary in order to reach 100% mortality of the invasive species. The dosing occurred at a junction box just ahead of the raceways, where water from the springs are mixed, and we provided product that they then calibrated with the use of some small metering pumps. This is showing us calibrating the pumps for the weighing the amount of material that would be pumped at a given pump rate, so that we would know how much copper we're feeding. And then those pumps were taken out to the junction box and turned on at a rate to yield that 90 parts per billion as copper. The flows through the hatchery are about 10,000 gallons per minute, and we were verifying the copper concentration present in the water using a Hawk method and instrument called a DR900. The method, the chemical method being the bisynchronizate method, which they also call QVER1. And as I'll explain in a minute in more detail, we later adjusted the dose rate down from 90 to the range of 30 to 40. So the product was fed at the source in that junction box, and then flowed through what they call 3 banks of raceways, banks A, B, and C. And then, as I mentioned before, the water returns back to the show pond on the left before discharging to the creek. And they did have enough individuals of the New Zealand mud snail present to be able to take some into the lab and try to learn more about them, and even keep a culture going there. That the hope was we could shadow the treatments in the raceways with treatments in aquaria in the lab, but it ended up being that they couldn't really keep them alive well enough. So in aquaria, so instead they just put them into double containment cages, like this one on the left, although I think subsequently they went to just bags, a mesh bag within another mesh bag to prevent escape, and then place those at various locations in the raceways. The study design was 10 individual New Zealand mud snails per cage, or actually they had 2 native snails as well, what they call the pond snail and the spring snail. And so they included those in the study design. So 3 snails total, 1 being the invasive and 2 being the natives. And they had 10 individuals of each snail per cage, 2 cages of each species in each raceway, and a total of 6 raceways. So 120 individuals of each species across all the raceways. This is a photo of the trout show pond. It's about 1/2 acre. And then this is a photo of same pond, just from the other angle, looking back. And at the bottom, there's the transfer structure that moves water from the show pond into Oak Creek. That's Oak Creek where it discharges. So I mentioned the initial dose was 90 and then later turned down. That's because they did get some fish mortality. It was substantial, about 20% of the hatchery stock. It was mostly the brown trout. They seemed to be more sensitive than the rainbow trout. But it was a bit of a surprise to me because we had the data from the lab showing it should be safe up to 240 parts per billion. We were wondering if it was confounded by other factors such as crowding. I'm sure many of you have fish tanks in your homes. I have a saltwater fish tank, and I've learned the hard way that you lose a lot of fish just to stress. And you know, once you get a couple factors together, fish can die pretty easily just from stress. So the operators did mention that once they released the fish to more open, less crowded raceways, they did recover. But out of abundance of caution, the dose rate was kept down at 30 and then just gradually raised back up to 40, which is where it has been in all their treatments since then. This is just to show a little bit the density. This is a quick video that will allow you to see just how crowded it was. So they're packed in there pretty tight. So during treatment, the mortality that I mentioned occurred just in the first 12 hours after turning it on. And then after that 12 hours, they turned it down to 30 parts per billion, half a part per million as product. And they just ran at that half a part per million as product continuously until the product ran out, which took 50 days. That's the product there on the left. It is a 275-gallon tote that's approximately 4 feet, a cube of 4 feet on each side. So here's the mortality. Mortality was judged on the basis of either being an empty shell or being, you know, really unambiguously moribund, you know, right at death's door. If it was borderline, it was considered alive. They did assess this mortality after transferring the individuals to freshwater and allowing them to acclimate there for a few minutes, and then they probe them with you know, an instrument to try to see any movement or activity. And then after judging the mortality, they put all the individuals back into the same mesh bags and replaced them at their location. You can see that the pond snail, the green one, which is one of the natives, died more quickly than the others. And that was not too much of a surprise because it's the one that does not have an operculum, meaning it can't close up and resist the environment as well. Whereas the native page spring snail does have an operculum like the New Zealand mud snail, and it had similar mortality rates as the mud snail. The coordinator at the hatchery did comment, however, that although the pond snail died more quickly than the others, when treatment was turned off, it bounced back really fast and really well. So this is all written up in a paper. There's the citation. It's in Management of Biological Invasions. If you need it, if you can't find a copy or want one, let me know. I can send it to you. And that's it for that project. But I wanted to follow up with sharing a more recent experience. This is actually one that's going on right now in the state of Utah at the Springville Fish Hatchery. They produce, it's a little bit smaller than the one in Arizona. They produce 150,000 pounds per year, but it's also like the Arizona one, it's mostly rainbow trout. And they discovered New Zealand mud snails last fall and elected to do a treatment similar to the one done in Arizona. And it's going on right now. I think it's getting to close to 50 days that they're in to that treatment. That shows their hatchery building. This is the layout at the Utah fish hatchery. The water comes from a spring there on the right and then flows through a building that provides UV disinfection and filtration. And the EarthTec QZ is fed just before that building. And then the water flows through their raceways and then through the hatchery building. This is their dose rate of copper. The top line in purple is the calculated dose, and the blue and red lines are the measured copper concentrations further downstream. And this brought up a little bit of a discrepancy. These guys in Utah are basing their dose rate simply on the calculated dose, but when he called, Skylar Wolf is his name, who's running this project, when he talked to the folks in Arizona, they indicated that they were basing their dose rate not on the calculated dose of how much copper was being added, but rather how much copper they were measuring in the water. And I've heard a little bit different accounts from different people there, but if that's the case, then that could account also for some of the fish mortality, because as you can see here, there's an immediate consumption of copper. There's a difference between what you measure and what you know you added. And so if they were measuring 90 parts per billion during the fish kill event, then it's likely that they were really feeding something like 120 or 130 parts per billion. So this is just something to be aware of. I don't recommend chasing a dose, like trying to say, oh, we're going to target a certain concentration measured in the water, because it bounces around too much, and I just find it to be unreliable. If you try to target a measured dose of copper, measured concentration of copper in the water, you're going to drive yourself crazy, constantly turning up and down your rate, chasing a stable concentration. I think it's more practical to just decide on your, how much copper you're going to add, and then measure and report the residual copper that you can measure, but don't chase that number as much as just adhere to the amount you're adding. So here's the mortality that they're seeing so far at the Utah hatchery, Springville. You can see the control is low mortality. I think 10% is the highest that they've measured. Another improvement on the methods that they're using here is that out of an abundance of caution for effects from examining the specimens in the cages, they only examine them once and then they discard them. So it makes for a little bit more complicated statistical analysis, but they are seeing just 0 or 10% in the controls that they've examined so far. And then you can see in the raceways in the hatchery building, they're getting up towards 100% mortality. It seems to be taking a little bit longer than it did in Arizona. Maybe the water's colder, but I think the plan is just stay the course until they reach 100% mortality. So now that we talked about those projects, I'll tell you a little bit about the product. I mentioned before, it's comes in a tote, 275-gallon totes. We also have drums, 55-gallon drums, and smaller containers, 2.5-gallon jugs. It's a blue liquid. It's EPA labeled in all 50 states as an algicide and bactericide. It's registered in most of the states as a molluscicide. We add states as they get infested with quagga and zebra mussels. But now that we've got labeling that is a little bit broader than just quaggas and zebras, it's invasive mollusks or nuisance mollusks in general. We're up to, I think, 40 plus states for registration as a molluscicide. It's also certified to NSF standard 60, which means that it's safe for drinking water. You can dose it right at a drinking water treatment plant even. So for a lot of uses, there's really no special permitting required other than the standard permitting that would be typical of an applicator applying for algae control. Same level of permitting, and then just follow the label. Although we do like to know what people are doing and offer some recommendations to optimize the dose and cost efficacy. I wanted to mention some of the other species that we've worked with. A lot of this happens in the field, kind of stumbling across efficacy. I mentioned earlier that this started as an algicide, and people then noticed when feeding the algicide into a pipeline, out the other end of the pipe came dead zebra mussels. So we sort of stumbled on the fact that it worked for that. And now, years into that experience, we've gradually seen that, oh gosh, it works also on Asian clams. And it makes sense that it would work on mollusks in general. What we don't know as much about is exactly what dose and for how long the exposure needs to be for each species, but stands to reason that for most mollusks, there's going to be some dose and some exposure period that will work. So one of those examples is with the Faucet Snail, and there was a nice piece of research done by Greg Sandlin and his group in, gosh, I'm blank, I think it's Wisconsin. And they tested EarthTec QZ against an invasive Bithynia tentaculata, and also against a native Faucet snail, and they were pleased to find that it was a little bit more toxic to the invasive than to the native. And so they're hoping to dial down on that a little bit more specifically and tease out that difference more so as to be able to treat for the invasive without harming the native. There's a Chinese pond mussel that was found in New Jersey. It's the only place in the entire US that this species was ever found, but it is an invasive. You can see how it's quite large. And so the folks who had control over that property, it was a series of fish ponds, aquaculture ponds. It had been shut down for years to try to prevent the spread, and they were eager to eradicate. And so a couple of years ago, we worked up a protocol for them, and we believe it was successful at eradicating Chinese pond mussel from this location in New Jersey. And then the last year or so, we've been working with the apple snail, which is a very serious pest in the South. It's considered the #1 pest of rice fields in the Philippines. And it affects catfish farming in Louisiana and Mississippi. So we've been working with a farmer, and crayfish farms also. So we've been working with a farmer in Texas who has a crayfish farm that the apple snails have infested, and we're working towards eradicating them from there. And also, we're just now in the process of being used, EarthTec QZ is being used to eradicate apple snails from some city park lakes in the city of Mobile, Alabama, and reports are it's working very well there. I don't have any pictures for the ram's horn snail, but that's another one that affects catfish farms, and we're trying to determine the dose rate and the exposure time needed to control those. But it all seems to be kind of in this similar range of 0.2 to 0.4 milligrams per liter. as copper. Depending on your non-target species present, if you've got sensitive fish present, I'd go more towards the 0.2 milligrams per liter as copper. You could even go 0.1 and then just do it long enough, whatever dose rate is safe for the fish, and then just do it long enough that it becomes chronically toxic to the mollusks. So back on our list of projects, I'll just share that for 2021, we have some upcoming ones as well. These are for zebra mussels and quagga mussels, but we will be eradicating from a 26-acre Illinois lake. It's a country club that has them in there. And then also from a lake that's owned by a homeowners association. It's 100 acres. There we're working more with knocking them back, lower dose, not to completely eradicate, but just manage them with quite cost-effective treatments around the shoreline, just enough to knock them back, but not eradicate them. The 60-acre lake in Indiana is intended to be an eradication. And then there's been ongoing work by USGS in St. Albans Bay of Lake Minnetonka. It's quite a large bay, 180 acres. Of course, Lake Minnetonka is a huge lake. I don't know how many thousands. It's thousands of acres. It's the largest lake in the Minneapolis area. And St. Albans Bay is just one bay of that very large lake, 180-acre bay. And the USGS has been doing some very interesting work to just suppress veliger reproduction there. So that's it for my presentation. If everyone's amenable, I'll take a couple minutes to just share some updates from that USGS project because I think it's interesting and informative to what I presume will be concerns or priorities of the audience here, primarily impacts on non-target organisms. So just, this is a presentation, or these are excerpts of a presentation by USGS and Angelique Dahlberg and Nick Phelps at the University of Minnesota's Aquatic Invasive Species Research Center. And then Jim Luoma started the project for USGS, and it was later taken over by Diane Waller, and Matt Barber's working on it also. But this, you can see there at the bottom is St. Albans Bay. It's fairly closed off from the rest of Lake Minnetonka, which makes it a nice place to treat. It doesn't get mixed, the water doesn't get mixed much with the rest of the lake. And then the control bay to compare with is called Robinson Bay. They're just above it. And their treatment protocol was something that I had recommended to them as this low dose for a long period. It's something we've used a variety of different locations successfully. Typically 5 doses, as this was 5 doses over a period of about 10 days. In this case, they targeted 60 parts per billion copper as their target concentration. And what they saw was the light blue bars are the control bay, Robinson Bay. The dark blue bars are the treatment bay, St. Albans. And on the left, you can see pre-treatment. There were about 4 to 6 veligers per liter of water. And then the day after treatment and 14 days after treatment, you don't see any dark bars at all because there were no veligers measured in the treated bays. So that was very encouraging. It was a successful treatment in terms of reducing veliger density. They also found the same 30 days and 90 days after treatment, whereas the veliger concentrations were quite high in the control bay. The absence of any dark blue bars there at all indicates that there were no veligers present in the treated bay 30 and 90 days after treatment. They also saw good results from treatment of the adults, or good results against the adults. The bars in that left picture or chart show similarly the absence of a dark bar in the September post-treatment analysis indicate that there were no live adults found in their sample area. And then you can see on the right as well, 2 months post-treatment, they found just a handful of live adult mussels as compared to before treatment. They had quite a few. And then let's see, this is 2 months after treatment. The adult mussels had declined by 2 orders of magnitude. And the following year in 2020, the treatment occurred in 2019. The following year in 2020, they found no live adult mussels at all in the treatment bay. So very successful, even though it was a very low dose rate, only 60 parts per billion applied over a period of 10 days, it was very effective. Now looking at the non-target impacts, this is zooplankton density. You can see pre-treatment ranged from 3,000 to 7,000 individuals per liter. And then a day after treatment in the treatment bay, you can see there was a pretty sharp decline, was down to less than 1,000. And then 14 days after treatment, the dark bar you can see is starting to creep back up. So it looks like they take a hit, right away after treatment, but they seem to begin to bounce back pretty quickly. And then as for other non-targets, they did use cages to monitor other species. The fat mucket is a native mussel. Then fathead minnow, fish, bluegill, largemouth bass, and yellow perch, other fish. And comparing the blue bars of the control bay with the black bars of the treatment bay, you can see that there was some loss, some mortality from the treatment, but not too extreme. And the most sensitive organisms were the fathead minnow and the yellow perch, but mostly was the fathead minnow. And then I thought this was an interesting piece of data to finish with. This is the last piece that I'm borrowing from theirs, but very interesting I found. This is the amount of copper that was accumulated in the tissues at the time of taking the sample. And you can see on the far right, the last bar is the zebra mussel. The zebra mussels have the highest concentration of copper in their tissues. The next highest was the fat mucket mussel, the native mussel. And you might wonder why, but the hypothesis is that the zebra mussels just they filter more water and they feed more voraciously than the other mussels. And that's what led to both higher concentration of copper in their tissues and higher mortality. So there was a little mortality with the, let's see, oops. Oh yeah, sorry, I forgot to mention. So the fat mucket mussel didn't suffer any mortality at all during the treatment. So that was exciting. I mean, we had to presume before treatment, you had to imagine, okay, if this is killing the invasive mussels, it's probably killing the native mussels too. But that was in the absence of having any data. But the exciting thing here is that they found that the native mussel did not suffer mortality. And we're thinking that it could be because the zebra mussel just accumulates more of the copper because it feeds more heavily. Okay, that's it for me. Thank you very much for your patience and attention. And if anybody has any questions, I'll do my best to answer them.
Okay, great. Thank you so much for your talk. We do have a couple of questions. One of them is the amount of copper in the water measured before adding in the copper dose in order to better monitor the overall dosage?
Yes, it's part of our routine or procedure to measure background copper. Background copper is usually very low, like 1 or 2 or 3 parts per billion. I've seen it as high as 15, 12 to 15 in some of the Great Lakes, like off of Detroit, in that area. But usually there is a little background copper, but in that range of 1 or 2 or 3 parts per billion. So when we're adding 30, 60, 100, the background copper is, it's small impact.
Thank you. One other question so far. Does the mortality of trout in response to the chemical differ among trout life stages?
That is a good question. I don't know the answer. When we did our toxicology studies through that third-party lab, they used a standard procedure, which I believe is fingerlings, small. Rule of thumb is that the juveniles or the small of a species is more sensitive than the mature. It may not be true 100% of the cases, but we tried to test the more sensitive ones to be conservative in terms of unwanted collateral damage and impacts. But I don't know for sure about the toxicity at different stages.
Okay, well, that is actually all the questions I have. If anybody else has any questions, feel free to speak up now. Otherwise, I will turn it back over to Jeremy for some closing remarks.
All right, well, thanks. I really appreciate it. Very informative. Appreciate your time joining us here. I'm sure we all learned something. And just some closing remarks for all the attendees. Thanks for joining again or for the first time. Remember that the webinar has been recorded and is available for later viewing at the website, as well as the previous webinars that occurred before this. And then one last plug is to join us next month for the 5th webinar, which will be taking place on June 30th. You'll see a flyer circulating around. And if you are registered for this webinar or past ones, you'll automatically receive a link. And if there are no other questions, thanks everyone for attending. Thanks again, David, appreciate it. And have a great afternoon, everyone.
I've actually got one more question that came on, sorry.
Okay, great.
Are the procedures outlined applicable to free flowing streams?
That's a tricky question. I would say, practically speaking, yes. However, from a regulatory perspective, that's a very different environment. We're not labeled for use in streams. So, we've done a lot of work in flowing waters in pipelines where we are labeled, and that's kind of our main niche. And I had a regulator come to comment to me, oh, well, if it works in a pipeline, it could work in a stream. Yeah, it's just there'd be a lot of other considerations. But as far as the practicality and the dose rate and all, yeah, I think it should be applicable or similar, except that you'd have many more non-target organisms, and you'd have other background demands from slime and algae and other things that would be kind of grabbing that copper as well. But it'd be a place to start. Yes.
Great, thank you. That is now all the questions that I've gotten, so good there.
Okay.
All right. Thanks again, David. Thanks again, everyone, and have a great afternoon.
Great. Thank you.
Bye.